So welcome to the second lecture. Do you have any questions from the first lecture which you discovered at home that you do not understand something? Okay, so we can go on. We were not very much in a hurry in the first lecture because it was introductory one, but I hope that today we finish this first week, or maybe tomorrow. We will see. So I try to recapitulate a little bit what was said on the first lecture. That the starting point, first of all, we just want to make some more, to create some new knowledge from linear algebra. Yes, now, this week. So the knowledge which was already in your head was that there is a linear space, something like this, n-dimensional and real. So important thing that finite dimensional vector space. And we discovered that there exists a new vector space which is called dual of the first one, and elements of this, some alpha, are linear mappings from L to R. First of all, we checked that really linear mappings from L to R make a linear space at all. Then we found a basis in it. So if there is basis EA in L, we constructed a basis EA with upper index in L dual, which is called dual basis to this, and the formula which defines the concept of duality is this one. So if we map a vector, basis vector, by this alpha, this is a particular alpha, we obtain a number which is delta AB, so sometimes 0, sometimes 1. Yes, this is the definition. So recall that this is a mapping, and this is argument of this mapping, and this is the element from R of this mapping. Now, if we have L and L star, from now it is a new topic. Yes, so we can repeat this procedure starting from the dual. That forget about L and take L dual as a first linear space. So we can repeat this procedure and construct dual of the dual. We will call it L double star. It is dual space to the L dual. Because we discovered that to any linear space we can construct dual. So including the dual. And so on. So actually, there is not just one dual space which is somehow connected with this original one, but there is an infinite series of dual spaces, which is rather unpleasant because of the reasons which are not clear now. But there is also a good news that these two spaces are in a sense enough, that you do not need these higher duals. And why? Because it turns out that here you have a mapping which is canonical, or natural, which means that this map is given automatically and there is no arbitrary choice. So there is a mapping for which you should not do any arbitrary choice. Then I will show you some example of mappings which need arbitrary choice in order to understand what does it mean that this mapping doesn't need arbitrary choice. So if this is true, so we should define what is some LV. Take V from L. LV should be from the second dual. What does it mean? That LV is a mapping So a grinder this is FV, yes? By definition, it is some dual of dual. So it eats elements of the dual and gives us real numbers. Yes, it works like that. That the arguments for this object, because it sits here, should be objects from here, by definition. And now we should define that, okay, what we obtain if we put the argument alpha to this FV? We should define this mapping. So we should invent some number, create it out of V and alpha. And there is a number, namely this one. So this is definition of this mapping. You see that there is no arbitrary choice. Well, I promise that I will show you an example where is arbitrary choice when I finish this. So given V and alpha, you can uniquely construct this number. It is no problem. There is no hesitation which alpha, which V or something like this. This alpha, this V. Yes, it is clear. Now, I leave it for the exercises to check that this is linear isomorphism. Yes? So this is first linear, and second, it is non-degenerate. So altogether, we call this linear isomorphism. So it is one-to-one mapping from this space to this space, which is linear. And it is exceptional. I mean that there are no choices. There is such mapping. So what we can do if such mapping exists, and we really do this check that it is linear and non-degenerate, yes? This means that we have an isomorphism, canonical isomorphism between this and this space, and that means that we can identify these elements, one element from here with some very specific element from here. Yes? There is a bijection. So actually, we can forget about these elements because whenever we need something from here, we go by this inverse isomorphism here and use this element. In any construction, when you need element of double dual, you simply replace it by the element of the L itself. Yes? And of course, such F is also here and so on. Between any starting linear space and the second dual to the starting linear space. And so this is the reason why really these two linear spaces are enough. We don't need the second dual, third dual, and so on, because when we need third dual, we use the first dual. It is by this isomorphism. So this is the first knowledge, that the original space and the first dual are enough. It is not true in infinite dimensions. In infinite dimensions, this space is interesting, really. Yes, it is non-isomorphic to this original one, or can be. But also it shows us something different, which will be useful for the following discussion, namely that you can interpret also a vector as a mapping. So we know that covector is a mapping by definition. Now the statement is that also vector is a mapping, namely from L star to R. So it looks strange, But how it is meant, there should be some interpretation of this. Namely, that we see that this mapping from L star to R is this grinder. And this grinder is called FV, not V. But because F is unique, canonical, and so on, we can just not write it. That we can write that it is a V which is this grinder. It is not V actually, but because V is uniquely connected with FV, because F is canonical, we can forget about writing FV and write simply V there. Yes? In this sense, it is not so simple, but in this sense, vectors also can be understood as mappings. The vector here should be actually FV, yes, but we write only V. There are at least two proofs, by the way, of 1 and 2. Well, in the book, there is very short example that prove that this is canonical isomorphism. So what should you prove? Linearity, it is easy, and then that there is no kernel. Yes, that we know that these two spaces are equally dimensional. So if there is no kernel, it means that it is isomorphism already. So, okay. In additional material, which I hope that I mentioned last times, that there is on my webpage something called additional material. It has more than 50 pages already, and very broad and very high pages with very small letters. So there is another proof, which I invented some time ago, and I liked it very much, this idea, which is completely different than this standard one. Namely that it is connected with how bases are behaving, that if here we have basis EA, here is basis EA dual 1, we know, yes? But now, when we start here and want to find basis here, we can use dual basis to this basis. And let's call it EI. Here, dual basis to this. Let's call it once more EI, and so on to infinity. And now, how this basis change when we change this basis? If we change this basis in the standard way, so this is the change of basis from the first year of linear algebra, yes, given by change of basis matrix. We computed during the first lecture, then dual basis then transforms according to the formula with a to minus 1, yes, with inverse matrix. Now, what about this matrix? This basis, sorry, yes? It also should change because this basis was changing, so also this basis should react somehow to it. And how it reacts? With inverse matrix to this matrix. But this matrix was already inverse matrix, so inverse of inverse A, B, this B, and so on. So you see that there is just switching A to minus 1, A to minus, and so on. But it means that if you construct an isomorphic, the mapping, this one, on basis, any linear mapping is defined if you know what basis does, yes? So let's define linear mapping by this mapping of basis. To the first small EA, assign the first capital EA, and so on, second, and so on. Yes. So it is now nice that this is already, first of all, this is isomorphism, yes, because the first goes to first, second to second, and there is equal number of them. So it is isomorphism. It is trivial. But non-trivial thing is that it is canonical isomorphism because if you change the basis by matrix A, this basis also changes by matrix A. So if they correspond originally, they correspond also after making primes. Yes, this is the main idea. This is not true for this change. So these two spaces, first of all, are not canonically isomorphic. They are isomorphic because they are n-dimensional. Each two n-dimensional spaces are isomorphic, you know, from the first year of linear algebra. But these two spaces are not canonical isomorphic, which has some proof. But we can have an idea, for example, that maybe this is canonical isomorphism, that put to the first vector basis vector, first covector basis, second vector basis, second covector, and so on. But after doing, combining with matrix A, this is something completely different because this changes with A and this changes with A to minus 1. So if in some basis you have isomorphisms, some isomorphism, in another basis you have different isomorphism by this formula. Yes? So think it over a little bit that, well, it is not proof that there doesn't exist canonical isomorphism. It only proves that this is canonical isomorphism, we see it, and this is not. Maybe there is some other, but the truth is that there is no other, yes? But the most natural other one is not working. There is an exercise in the book that check that this is not working. The idea is because they are different matrices, and simply if you want it to see it concretely, so do in two-dimensional space, you know that if you have some E1, E2, you can make a new basis by the sum and difference of these vectors. Maybe you know that E1 plus E2 and E1 minus E2 is a good basis also in two-dimensional linear space. So make this matrix and check yourself that it is visible, that it is completely different isomorphism starting from the original basis and after these linear combinations. So this doesn't work, yes, as a canonical isomorphism. As an isomorphism, it works. So now the most important idea from all this, except for that we can forget these higher duals in finite linear algebra, finite dimensional, is that this fact that we can understand vectors also as mappings. Yes? So that there are actually two grinders. Yes? One of them is called alpha. It is from the last lecture. And one of them is called V. So for vectors we have a grinder, and for covectors we have also grinder. So now the idea, let's do bigger grinders. Yes. So how it looks like, that what eats this grinder? Vectors. What eats this grinder? Covectors. Yes. So let's have an idea that we compose a big grinder, for example, for 2 vectors and 3 covectors. So V, W, alpha, beta, gamma. And after turning the crank, we obtain a number. It is clearly generalization of those two ideas, that if alpha is a grinder for 1 vector and V is a Grinder for one covector. Let us consider Grinder which is called T from the word tensor, which has several inputs for vectors as several inputs for covectors. For example, we see that 2 vectors and 3 covectors are here. Yes. So define a mapping formally that there are 2 vectors and 3 covectors. And it goes to real numbers. What does it mean, these times here? Is it clear? What is it? What? No. No. Cartesian product. So what is element from here? It is 5 tuple, or how is it called? N tuple is, well, something like that. Ordered 5 tuple, that vector, another vector, first covector, second covector, third covector. This is element of this set, yes? And map it to T, V, W, alpha, beta, gamma, which is already a number. Let's introduce such mappings. Yes, this is the idea. So both these grinders are special cases. Yes, the first is special case where one vector is inserted and no covector, and the second grinder is example that one covector is inserted and no vector. But here is, for example, 2 vectors and 3 covectors. You can understand that you can introduce such objects for any number of vectors and any number of covectors. But these 2 grinders are not only mappings from vectors to real numbers and covectors to real numbers, but they have some special properties, which is linearity. They are linear mappings. In such case, when you have several vectors and several covectors, the natural generalization is that it should be multilinear. Yes, it means that it is linear in each slot, separately. So if you fix, for example, all objects except for the alpha, and here you put alpha 1 plus lambda alpha 2, the result should be the result with alpha 1 plus lambda result of alpha 2. So it is linearity in this slot. And this mapping should be, by definition, linear in all slots, both vector slots and covector slots. There are no other types of slots. There are just 2 types of slots. Why? Because this doesn't exist in a sense. Yes. If there were no canonical isomorphism, we should invent grinders for any objects up to infinity. Rather sad story. Yes, but now the story is not sad because we need only 2 types of these linear objects, vectors and covectors, nothing more. So we introduce these multilinear mappings as possibly interesting objects. So, first of all, we have 2 examples. Do you know some third example which is well known from your course of linear algebra? Yes, and it is what kind of mapping? It is a bilinear form. Yes, so bilinear form, well-known object from linear algebra, I think that's 2nd semester perhaps, is a special case when you have this part and just this part. Yes, it is a grinder that you insert bilinear form, special case, 2 vectors and a number outside. By the way, there exists also interesting linear maps when this output is not a real number, but for example, a vector once more. Yes. So 2 vectors inside, 1 vector outside. It is an example of vector product in physics usually used. But here will be always for us now the space R. The case when here is something else, some other linear space, is treated in the book in section 6.4 if you are interested. And it is interesting case, but not for the beginning stage. Yes, it is very much used in chapters in the book 19, 20, and so on. They are called then vector-valued tensors, but here are just scalar-valued tensors. Well, so now we want to know something about that. Why are there interesting these multilinear maps? These multilinear maps are called tensors. So this T is a tensor. And namely of type, how many? 2 vectors, so here is 2 and here is 3, perhaps. Yes, I hope so. Tensor of type 3, 2 is multilinear mapping which eats 3 covectors and 2 vectors. So you understand that we can introduce tensors of type RS for positive integers. And also there is an exception that what about the case 0, 0? Yes, it is such a strange case, exceptional, that do not put the idea, no input, and output of R. So this grinder knows this output without knowing the input, so it is just the real number, by definition. Well, what I said is just an idea behind, but definition is important. The definition is the tensors of type 0, 0 by definitions are real numbers. Yes? And we also will have some notation for it. This is the set of tensors of type PQ for the linear space L, started from the linear space L. Yes? So for example, this T here is from T3 to L. And bilinear form is what tensor? Which are numbers for bilinear form? 0, 2, exactly. Yes. So we know already several types of tensors. At least we knew vectors and bilinear forms. Yes. I believe that you didn't have these covectors or linear forms. I don't know, maybe you had it on the course. Did you have in linear algebra?
I'm not sure, but it was in the book.
Ah, in the okay. So in the book, yes, it is. But it is a little bit strange thing that the simpler object, linear form, is usually met only after the more complicated object, bilinear form. Yes. Okay, so now we go to basis, components, and this thing, how they change, and so on. So, first of all, what are components of this tensor? And that then will be also then true for vectors and covectors as special cases. Yes? So, for example, let's make a simple object, some t, not to write 5 arguments, but for example, 2, 1. Okay, 2, 1. another case, not this. So we need, there are two covectors and one vector inserted. Now, we know already basis for vectors. We fix some basis, this one. This is any one, but fixed it. So the vector can be decomposed in this way. We learned on the first lecture that there exists a dual basis for covectors. So let's decompose here with respect to the dual basis. And the same here because it is also covector. So imagine that you put these decompositions inside and then use bilinearity, not bilinearity, but multilinearity, three linearity in our case. It is linear with respect to this, this, and this. So what does it mean? That is components of vectors and covectors jump outside. So we'll have VA alpha B beta C and tensor on EA or EB and EC. So what we need to know if we want to use this mapping, to actually do it, we just need to know these numbers. This is characteristic of the mapping. And this is characteristic of the inputs, these numbers. Yes? So divide it. Let's call this T, A, B, C. There are some numbers computed out of tensor and of basis. So what choice is made there? Just this basis. Yes, this is the only choice because these are automatic. They are dual basis. So this is the only choice for this set of numbers. So we see that there is a simple formula, BCA, VA, alpha B, and gamma C. When you want to compute the value of the tensor on some particular arguments, you need to know components of these arguments, which are vectors and covectors, and then you need to know these numbers, which are called components of the tensor. Components of T, tensor T, with respect to the basis EA. So components, both on vectors, covectors, and also for tensors, depend on the basis. If you change the basis, you will have other components of vectors, of covectors, and of the tensor. But this number should be still the same, because this number is abstract value of abstract tensor or and so on. Yes? So here is no choice of basis. But if you do the choice of basis, you will have this result. So if you change the basis, each bricks here are changed, but the complete house is still the same. So from this, we can now easily compute that we already know how these guys transform, because it was on the first lecture. And now we can find how the components of the tensor change. So what are T, B, C, A primed? Component with respect to primed basis, which is A, B unprimed. So what is it by definition? because this is the definition of components, of original components with respect to basis EA. This is by definition the same thing with primes inside. EB primed and EC primed. Now, this is what it is. Matrix A something, well, ABC, for example, I, EI, A to minus 1, B, J, A, J, and here A to minus 1, C, K, E, K. So what we have? We have three matrices, two of them inverse, and original components, because what happens when you insert all this decomposition into these slots, that these matrices are numbers. They jump out, so they are here. IA, BJ, and where is CK? So they are already outside. And what is inside? T on EI, EJ, and EK. And this is nothing but JK, so it is IJK. So the formula looks like this. So what we see, that for each lower index, this A, you have matrix A. We have just one, but if there should be more, for each one will be matrix A. For each upper index, for example for B, you have inverse matrix with B as upper index and some summation index down. And for the second upper index, you have this matrix with C and another summation index. And after this, you have original components, non-primed components of the tensor. So the rule is clear and simple. Yes? Have a look how many components has your tensor, and when you want to compute primed components, just put enough A and A to minus 1 matrices with right components, and after that, put the original components of the tensor. Yes? So it is simple. Let us check whether it works for vector and covector. First of all, VA primed. It is just one upper index. For upper indices, we have inverse matrix. So here should be inverse AB VB. What about covector? Is another special case. One index down, so matrix A. Okay, so it is from the first lecture, we know that it was the case like that. Now we see it in bigger perspective, yes, in the perspective of tensors. And also, what about bilinear form? So bilinear form from first year. Two lower indices, so two A matrices, A, B, some CD, and B, CD. Now, because this is an object with two indices, it can be treated as a matrix, exceptional case, yes. Whenever you have just two indices on your tensor, it can be written as a matrix. So when you treat it as a matrix, there is some matrix multiplication here. And what kind of matrix multiplication? What matrix here has A as first index? And what matrix has B as the second index? This is maybe hard because there are two types of matrices. You see that this is matrix like you know, and this is matrix like we use also in this lecture, that upper and lower index as the first and second. Yes. So, for example, on this matrix, the first index is C, but we need A index, and it is as a second here. So, what helps in this case? On what matrix A is the first index? Not transposed. So it is A transposed, AC, then goes CD, so B, and finally A, and from this you have AB. And maybe you know this formula from the first year, yes? So we just check that it works, yes, that if you believe this formula from the first year, it was practically derived in a very similar way, yes, by something like that, but not speaking of tensors, probably. Yes. Now we see that it is a special kind of tensor. What about the tensor, some C, of type 1, 1? What is the formula for 1, 1 tensor? There is one usual matrix, one inverse matrix. Here should be A, because of the upper index. Here is it okay or reverse? Lower index is okay. So here should be B. Sorry, and here should be A, and some CD and CD. Because there are two indices, once more, it is a matrix multiplication. And what type of matrix multiplication? A is here as a first index. So the first matrix is A2 minus 1. D is then, and here is once more A. So maybe you remember that in the first year linear algebra, you have both transformation formulae, both this and this. This was transformation of matrix of bilinear form. And what was the transformation rule which corresponds to, or what object behaves in this way that this is its transformation rule? Do you remember? Sorry? Between inside one vector space. Yes, now. So linear maps or linear operators in L. This is the formula that if you have linear map from L to L, then it has a matrix, and the matrix transforms with respect to change of basis in this way, exactly. So you see that it is slight difference. Here is A2 minus 1, and here is AT. Sometimes there is no difference when it is. In which case, the formula is the same, actually. So actually the question is, in which case, transpose matrix is equal to the inverse matrix? No. Sorry? Orthogonal, yes. There is definition of orthogonal matrices is that ATA equals 1 equals AAT. That means that transpose matrix is the same thing like inverse matrix, yes? And what is the practical situation when you meet orthogonal matrices in your life? Most usually from rotations. So if you study how tensor components change with respect to rotations, so with respect to orthogonal matrices, there is no difference between this formula and this formula. And this often happens in physics, that in physics we frequently study how this behaves with respect to rotations. Then you cannot distinguish between this object and this object. You cannot distinguish between linear operator and bilinear form in this situation. In more general situations, you can distinguish by this fact whether there is A2 minus 1 or A transposed. And this already shows something, that yes, it is true that linear operators in vector space L, that means these mappings, have the same formula like our tensors of type 1,1. Yes? We introduced tensors of type 1,1. You introduced in your linear algebra course linear operators. Now we computed transformation of components. You computed some 2 years ago transformation of metrics of linear operator, and we discovered that it is the same thing. What does it mean? That there is an intimate connection, so to speak, between linear operators and tensors of type 1,1. It is something similar like this dual of second dual with respect to L. It doesn't mean that tensors are by R linear operators. It means that there is a canonical isomorphism between linear operators and tensors of type 1,1. But practically it means that they are the same. Yes? So when mathematicians said that this is the same thing, they mean it is canonically isomorphic. Yes? If it would be not canonically, it is not the same thing. But if it is canonical isomorphism, you can say that it is the same thing practically. You have an exercise which will be on the recitations that find this explicitly these isomorphisms, that you have a linear operator, some C. Now you want to construct the tensor of type 1,1. Yes. And the question is, if this is given, C, how to construct this tensor? They are not the same thing, but you should construct the canonical isomorphism between tensors of type 1,1, that means to answer this question, what the number is here, construct it out of this C somehow, and of V and alpha. Yes? So this is something from C alpha V. And this is very easy task to find this, especially if you have a look to the book where is hint. Yes, that this is the answer. But in spite that you know the answer, you should check that it works. Yes, that if you use this formula, which is canonical isomorphism again, that it really works. It is linear and all details. So it is useful and nice exercise, and it's quite simple. And it is strange that these tensors of type 1,1, in particular, these tensors, actually can play three roles. First of all, mapping from L to L. Then mappings from L star to L star. This means that linear operators in the dual space. This is linear operators in the original space. Linear operator in dual space is something different. But there is a canonical isomorphism also of this tensor to operators here, and also to operators here. And the second is the official definition. Official definition is this mapping. Yes, this is the definition of tensor of type 1,1. So this is very important, that if you have one tensor, it often serves many purposes. The same tensor can be used as this mapping, and this mapping. This is, of course, because this is official one, but the lesson from it is that if you have some official definition of this object, it doesn't mean that it has no other role. it can be also defined another way. Yes? For example, like that, in this case. In general, we should be prepared that the same type of tensor can be understood as a lot of mappings. And it is very important because why we try to learn tensors? Because for us, they are important in physics. For some guys, they are important in mathematics. Yes? But if they are important, you can meet them somewhere. And you can meet them in any of these versions. So in some physics, you meet tensor of type 1,1 as linear operator. In another physics, you can meet the same tensor as this mapping. Yes? So you have to be prepared to understand that here is a tensor of type this and this in this situation. Maybe you remember that when we studied tensors in second year theoretical mechanics, we had several tensors there. One of them was stress tensor and strain tensor and so on. They have some natural introduction that because of this phenomenon, we have a tensor here. Then have a look to this phenomenon and try to understand which type of tensor is there actually. It is good exercise for physicists. Yes? And for mathematicians, if you see somewhere a tensor, try to understand what type of tensor it is. The same type of tensor can be found also in another situation, in another row, so to speak. So this is very important that use or be prepared to understand all roles of given tensor because you never know which role you meet in your practice. So we should not be some fundamentalists that for us tensor is only this. It is a bad idea. Also, this is tensor, also this is tensor. And also another fundamentalism is here that some people don't like these component expressions because they are big scientists, and big scientists do not like such dirty things like components and so on. So it is not a good idea. Also, this approach to the problem is good. Also, this approach to the problem is good. So you can do something with many indices, and it can be okay. You can do something in abstract way, it can be okay. So you must be prepared for several points of view on the same thing. Yes? This and this is the same thing, said differently. So be prepared to understand it when you read it somewhere and to use it. Because for some problems is better this approach, for other problems this approach is better. So you must be prepared at least for these two approaches. Now, I have a look, what is the tensor of type we know, its components, their transformation we know. Now, tensor operations. There are some operations which are called tensor operations. So what can be done with tensors in order to obtain another tensor or something like that? So we already know one no, we do not know yet. Imagine we have t and tau from, say, t1, 2, L. So two tensors of type 1, 2. We can then construct their linear combination. Special case was not of 1, 2, but special case vectors and covectors. We already know that this can be done like here I will define. So linear combination. What does it mean? We want that this object should be once again from this tensor space 1, 2. Yes? It should be also tensor of type 1, 2. So tensor of type 1, 2 eats one covector and two vectors. So we should be able to answer this question. What number is here? Definition. Put all arguments to t put all arguments to tau and make linear combinations of the result. Yes? This is linear combination in R, in the target space of this mapping. So what should we do? This is proposal. That I think that this could work. But if you study this, you must check. Is it good definition? Is it really free linear mapping? Yes. And so on. Check that this is good idea to define linear combinations of tensors by this way. Maybe, or not maybe, but sure it is clear that this 1, 2 is not important in this idea. It is just not to write from 1 to Q and from 1 to I don't know what, complicated formulas. On this case 1, 2, you see everything. You can if you have some examination and the question will be write it for 714, I believe you are able to write this formula for 714, yes? So this is the idea which, if it works, check that it works, that this is a linear space. And not only for 1, 2, but T, P, Q, L is a linear space. So tensors of given type form a linear space. What is the dimension of this space? In order to find dimension of some linear space, you either find the basis, which will be done here, but I don't know, we will see whether basis will be today. But other way is to compute how many numbers you need to specify one particular vector there, yes, in this vector space. Because the number of real numbers is actually number of components, because you want to need components with respect to some basis. So either you know the number of basis vectors, or you know the number of components. This is the same number. So here we yet do not know how to construct the basis. We will do it. But for construction of basis, we need another tensor operation, which is called tensor product. It will be in a moment. But without basis already, we can say that how many numbers you need in order to specify one particular object here, one particular vector. What we need is a set of all components. So if we have a general tensor from, or this is not, which correspond to PQ tensor, they are components of some PQ tensor. So how many components we have? We have P indices here, Q indices here. By the way, this is the interpretation of PQ. This is the way how to put it to your memory, that here is the number of upper indices on components. And this is the number of lower indices on components. Okay, so altogether we have P plus Q components. Some of them are upper, some of them are lower. It doesn't depend from the point of view of dimension. And each component can have n possibilities from 1 to n, because we are in n-dimensional vector space. So I think this is the right formula, yes? N2 P plus Q is the dimension. So for example, what is the dimension of the space of bilinear forms? So bilinear forms are special cases with P equals to 0 and Q equals to 2. So P plus Q is 2. And therefore, the dimension is n2, 2, n squared. And this is okay because it is exactly the number of real numbers in a square matrix n by n. So it is correct answer. Or we can check a famous tensor we already had in elasticity theory last year. It is CABCD tensor. Remember that it is in three-dimensional space, so n equals to 3, and there are 4 indices. So 3 to 4th power, it is 9 times 9, it is 81 components altogether. But actually there are some symmetries, and because of these symmetries, the real actual number of independent components was less. But without the symmetries, we know also from this formula that the number of components is 81. So 3 to the 4th power. Well, what time we have to the end? I think that is enough time to introduce the last tensor operation, which is called contraction. Denoted by C. And it is a linear operation from PQ tensors to P-1 Q-1 tensors in the same vector space. So on the left we have P slots for covectors and Q slots for vectors, and on the right hand side one less. So for example, if we have P1 and Q2, then after this contraction from 1, 2 we get 0, 1. So we have the result just with one lower index by definition. And now how it is defined? Any tensor from this PQ space has several slots for vectors and several slots for covectors. Here are the slots for covectors. Q of them are for vectors and P of them are for covectors. And the tensor is multilinear in all slots, by definition again. Now, the procedure of contraction consists in inserting a basis vector, EA, to one slot of vectors. It depends on which slot we put it, the contraction is then different. And in one slot for covectors, now this is important, we put a dual basis, element of dual basis, which is EA. So because we fill one slot for vectors, the resulting tensor has one slot less, because one of them is filled, and also the slots for covector, they are one less than it were at the very beginning, because once again one slot is filled. But the remaining slots are still there, and multilinearity says that with remaining slots it is still linear independently of the other slots. So we see that doing this procedure we get really a tensor from PQ, we get P-1 Q-1. So PQ should be at least 1, 1 in order to be able to do that. And now the only last interesting question is that whether it makes sense, that whether it depends on the choice of basis or it doesn't depend. If it depends on the choice of basis, it is not very interesting operation. But if it doesn't depend on the choice of basis, it is very interesting operation. So we should compute that what happens if we put there some primed basis as a basis for vectors and then dual to this prime basis, so primed dual. Whether we get the same result as if we gave it original vectors and covectors. So the primed basis is given of vectors and covectors by well-known formulas. Remember that the dual basis transforms with respect to inverse matrix. And now, because of multilinearity, so linearity with respect to these two slots, these matrix elements can jump over. So from the first we get ABA, and from the second AAC. Well, actually BA. Here should be A, and then C. And the tensor computed on unprimed basis, so EB here and EC here, but already unprimed. Because this is AA, so it is matrix multiplication of this matrix and this matrix element BC. But this matrix multiplication gives you unit matrix. So it is unit matrix element BC. That means delta BC. Delta BC makes BB or AA or CC. Yes? So the first object. So in spite of the fact that we make a choice, it doesn't depend on the choice. If you make another choice, the result is the same. So it is very interesting operation. And now how to do it on components. This is abstract definition. You see that I did it on these mappings, tensors as mappings. Now, what about components? Let's do it for just 1, 2, yes? 1, 2. So we have this type of components. So 1, 2 means 2 vectors and 1 covector. So let's make a choice that this vector slot and here is no choice because there is just 1 covector. So what is this? This is T, A, B, C, V, B, W, C, alpha, A. Now, what is this? Expand this vector with respect to basis. Here is AA, so some B, VB, EB. Then put components outside. And what we get? T on EB, EA, EA. But what is this by definition? T, B, A, A. So what happens? That first of all, in the original tensors, we had 3 arguments, 2 vectors and 1 covectors. After doing this procedure, this contraction, we have just 1 argument of the resulting tensor. There is no place for anything else because this place was spent for this basis. Yes? So there is just 1 argument, and this argument is vector. That means that the resulting tensor is of the type 0, 1. So it has 1 lower index. And we see that really this object has only this free index. Yes? So from ABC, we went to TABA. So how the contractions look like in the language of components, then you make a summation of one upper index and one lower index. Yes, this is the clear algorithm, how to do it. We already see that we have two possible contractions, for example. We can do this contraction or this contraction, in principle, and the results could be different in general. Yes? So if you say that I did some contraction, if it is not clear from the context, sometimes it is clear, but often it is not clear, and you must specify what do you mean. For example, it is not to be understood now, but there is a very famous tensor which is called Riemann curvature tensor. It is the object which is studied in 15th chapter of the book. So Riemann curvature tensor is of type 1, 3, as we see. It is one upper index and three lower index. And now, this particular contraction, so A, B, A, D, summation over AA, gives you a 0-2 type tensor, which is called Ricci tensor. It is historically created sometimes, more than 100 years ago, and this is something fully describing the concept of curvature, and this is some not so big information, some smaller information about the curvature in the Ricci tensor. So this is just example that in physics, yes, that there also in mathematics. Also, of course, the curvature concept is mathematical concept primarily, and only in relativity theory they discovered that it is also very important for physics, but it was prepared in mathematics originally. Yes, so this can be done, and by the way, there are just two lower indices, so there is no possibility of further contraction, because in order to do contraction, you need one upper and one lower index. You can check that if you put two E's in the vector part, EA, it doesn't work. So this cancelling of this A matrix only happens when you have one A and one A to minus 1. In order that this operation should be interesting, these matrices should cancel here, and it is only possible if one of them is inverse and one of them is original. So you cannot do the same trick with the vector part and with the covector part. You only can do the contraction one from vector part, one from covector part. Yes? And here, for example, we have just these indices left. Both of them are down, so it is not possible to do further contraction. But we will come to the fact that there is something like metric tensor, and there is something like racing indices. So after some introducing of other structure, it is possible to make other contraction, yes, further. But as it is not possible. This is the only step from here to here. Actually, yes, you can do also this contraction and this contraction. And the question is why we are not doing those contractions. The answer is in chapter 15. Yes? Here it is not interesting. But I want to stress that here are three possible contractions, and only one of them is interesting somehow. Okay, so contraction as important operator, and to the very end, probably we will speak of tensor product. As a further tensor operation, very important. Tensor product, for example, gives us the basis for tensors, which we still do not have. We know what are components, but we don't know with respect to what basis it is. So, once again, two tensors, some tau, but of arbitrary type, but not to do it very messy. Let's have this from 1, 2 type, and this from 1, 1. Yes, so tensor tau, tensor T is prepared to eat two vectors and one covector, and tensor tau is prepared to eat one vector and one covector. By this basic definition. Right? Now we construct tensor denoted like that, which eats all these arguments, 5 arguments, 3 vectors, but you see that there is maybe some u and beta better. Yes. So all vectors first, then all covectors, and the definition is that by definition this is the product of these two numbers. So what does it mean in this particular case? That this product is a mapping from T, I will not write L, but T1, 2 times T1, 1 times, in Cartesian sense, 2 T2, 3. So notice that here the upper number is the sum of two upper numbers here, and the lower number is the sum of these two. Or you should use sum of the all arguments. This is the reason. Yes, and it works according to this formula. Formally, it is this mapping, and this is official definition. First of all, does it work? Is it really a tensor? This is the first question. That if this is a tensor and this is a tensor, is it really true that the resulting object is a tensor? So the question is it really multilinear? It is linear with respect to all arguments. So check, for example, this argument. Linearity in W when fixed, all other fixed. Yes? W is here. So imagine you give a linear combination W plus lambda W tilde. Yes? How it reacts, this expression. Here, it is W is inside tensor, so it reacts properly, yes? As tensor should, linearly. And then it is multiplied by some number which doesn't depend on this W. So it is linear. I hope that it is clear that this is true for all 5 arguments. That, for example, beta is here, it is in tensor, and it is multiplied by some other number. Yes? Think it over, that this really produces a bigger tensor for small tensors in general. Now, how it is done in components? Because these tensors are of type 1, 2, and 1, 1, the original T has this type, these components, and the tau has some ABC, D, E, say. Yes? So we have this tensor and this tensor written in components. We know all components. How to construct components of the tensor product? So check. What are components of this result? They should be A, D, B, C, E. Yes, because 1 gives 2, so there are 2 indices upper and 3 indices lower. What it is by definition? We should use the definition of components of the tensor now. These indices are the value of the tensor on the basis. B, C, E, and semicolon AD. This is here is definition of components. Now, definition of tensor product. Another definition, that the rule is start from the left of both groups, vector and covector group, and put the arguments to the first tensor until it is filled. So this tensor needs two vectors and one covector, so these two vectors and these covectors go to the first tensor. And the rest goes to the second one. B, C, E, D. Yes. Now, what is it? This is T, B, C, A, and this is tau, E, D. So what is the rule? That just multiply these two numbers, said clearly, yes? But with different indices, no summation, yes? So the resulting tensor has all indices which are present on the first one, on the second one, and just put them in this way. You see that also the order is important. Here is AD, AD, BCE, BCE, yes? Because the rule is as it is, it always be okay from the point of view of number of indices. Yes, that the number of indices here and here should be the sum of the number on these two upper and on these two lower. So this is also possible to define tensor product through this rule. It should be then possible to prove that this rule in components corresponds to this rule on general arguments. But maybe simpler is to show that if you define it as this, it is clear that it is linear in all arguments. That means it is a tensor operation. Yes? Fine. Now imagine that we already understand this, and we produce such tensor. From where it is? Is it from something of this type? Where from is this object? It is a what? It is a covector. It is a basis of covectors. Covectors are 0, 1 type tensor. Yes? So this is from 0, 1, L. This is the same type of object, once more, 0, 1, L. So necessarily, because we did tensor product, this should be from 0, 2. What are 0, 2 objects? Bilinear forms. So this is a bilinear form for each A and for each B. It is not just one object. It is for each A and such objects and each B. So altogether, n squared tensors of type 0 to L. So first of all, this is the number of them. Very important thing that they are tensors for each A and B. And all of them are of this type. Now, if you take any tensor, B of type 0, 2, we can check that this can be decomposed with respect to those tensors. That B is BAB, EA, EB. And they are numbers. So it is similar like we decompose vectors with respect to vector basis, covectors, last lecture, with respect to covector basis. Now we are prepared to check that this is the decomposition of tensor of type 0, 2. And it is, if this works, it is clear that we know the way how to decompose any tensor. Yes? For example, 1, 2, T is 1, 2 is T, A, B, C, E, B, E, C, E, A. So I do the computation here. If, well, I start the computation here and check that, then check that you understand how to do the same thing with this tensor. So we want to prove this, that if you have a general B, tensor of type 0, 2, that means bilinear form, you can write it in this way for unique BAB. So it is a decomposition with respect to the basis. Then we will see that this is a basis of tensors. We know, by the way, that n squared is the dimension of the vector space. So if we found n squared basis vectors, maybe basis vectors, it is compatible. Yes, that we need n squared basis vectors. Here are some basis vectors of the numbers n squared. So it is possible that it is a basis, in principle. But how to prove it? Prove it. Once more, like for covectors, we made a similar proof that this is true. Yes? And do you remember what was the idea? That what we are proving, what object is here and what object is here, important for making the proof.
We let it act on two vectors and say they do not represent the same.
But what is a tensor of type 0, 2 by definition? It is a mapping, first of all. It is a mapping. So, and is this a mapping? For each A and B, this is tensor of type 0, 2. That is a mapping for each A and B. This is linear combinations of such mappings, which was proved that it works. It is a linear space of mappings. So this is also a mapping altogether. So what we want to prove, that this mapping is the same like this mapping. And how it is proved? By general arguments. So we want to prove that this, because it is bilinear form, so tensor 0, 2, U, V, now question mark, B, A, B, E, A, E, B, on U and V. Yes, so this is the question. If this is true for any U and V, then these mappings are the same, so these tensors are equal. And within the check of this, we will see how to compute this BAB. There will be a unique formula. So first of all, here, for example, what is how to do it? The definition of linear combination, we have to look, is that this argument go to this part of tensor, and this will be in front of the expression. So here will be BAB as numbers, and now EA, EB on UV. This is, here I used definition of linear combination of the tensors. Now you have definition of tensor product. There are two arguments, there are two guys here. By definition, this argument should go here, and this argument should go here. Yes? This is the definition of this symbol, of tensor product. Now, what is it? For example, EAU. By definition of what is EA, sometimes on the first lecture, this is UA. So nothing but definitions. So altogether, what is here? BAB repeated. And now, EA on U, it is UA and VB. And check that by decomposition, UAEA, VBEB, check that this is the same on the left-hand side. by bilinearity, ui and vb goes out, and the rest is BAB by definition. So I think 5 definitions maybe are used there. And try to do this expression. If you are able to do this expression, including that you find how much is it, the ABC, something like that, what is BAB? BAB is B on EAEB. So they are components. We already introduced what is, what are components of tensor. This is the very end. So, sorry, BAB is B on EAEB. This is the result, yes. If you use this BAB, then this is true. So this is the end. Are there questions? Okay, so tomorrow we will speak of metric tensor primarily, and maybe we will go to some further material. I don't know, but I expect. It is not too much. I think that it is not for one full lecture, this linear algebra. Okay, so no questions for today? No. So thank you.